Alrighty, hi everyone. I'm just kind of going through your chat requests right now. So welcome to the final review. I see a lot of, so as I'm just scrolling through this, it seems like we want to do some sigma bonds and pi bonds, and just like periodic trends and shapes and stuff. So a lot of chapter 7 or the end of chapter 7. And then going back to chapter 5 in terms of like gas laws and stuff like that. I think we'll start with Lewis structures and pi bonds and polar bonds and sigma bonds there. And then we'll go back to gas laws if that is okay with everyone. Just kind of looking through what you're asking about. I think that'll be the most beneficial for us. And then as I'm going through those two kind of main topics, I'll make sure that I touch on the topics that you discussed in the announcement a couple, like 30 minutes ago or so. Okay. I am currently making my answer key for the practice problems I put out yesterday as well. So those should be up with like an hour after this gets done, and then this recording and any notes that we take today will also be posted after that as well. Okay, so if there's, and then if we don't cover anything in this hour right now, feel free to email me and I'll be happy to answer them before the exam and anything like that over the course of the rest of the day. Okay, so let's start with, we'll do like sigma, pi bonds, Lewis structures, and all that fun stuff there. I personally do not know what's going to be on the exam. I don't see the exam being created and I don't see it beforehand. So I don't know exactly what's on there. So sorry about that. Okay. So let's start off with sigma and pi bonds, talking about Lewis structures, talking about structures in general. Okay, so when we have a bond between two elements, we can say it's something like this. Okay, if we just have this structure here, anytime you just have a single bond, does anyone know what that's going to be called in terms of sigma or pi bonds? Good, so this will be a sigma bond. And if you see a symbol for this, this is going to look like the circle with the hat on top. So that's going to be a sigma bond. Anytime you make one bond between two elements, that'll always be a sigma bond. If you have a double bond, like we see with between the C and the O, or even a triple bond, the first bond you make will always be sigma, and then the next two will always be pi. So how many sigma bonds do we have in this double bond up here? We have one sigma bond. How many pi bonds do we have in that double bond? Good, we also have one pi bond. Okay, the first one, we'll call it the left one, would be your sigma, and then the right one would be your pi bond. Okay, so when we have a double bond, we have one sigma and one pi bond. What if we had a triple bond? How many sigma bonds are in a triple bond? Good, there's one sigma. There's one sigma bond. How many pi bonds do we have? Good, so here we have two pi bonds. Okay, the first one will always be the sigma, and the second one will always be a pi, and then the third one will always be a pi. You won't have 4 bonds between anything, so you only need to worry about 1, 2, and 3 bonds between an element. Okay, so if we're looking at, right, we just do this. we said that there is one sigma here. I don't know why one sigma here. We have one sigma and one pi. And here we have one sigma and 2 pi. Okay, what questions do we have on sigma and pi bonds now? Anything on sigma and pi bonds? Yep, so on the homework and just in terms of like shaping of stuff, we're looking at the orbital overlap between a sigma and pi bond, and that's what causes a sigma or pi bond is the orbital overlap. The first one, it was 3 sigma and 1 pi. Yep, so in total for this guy here, we had 3 total sigma bonds and 1 total pi bond. Okay, so what makes something a sigma or a pi bond is how those orbitals overlap. So what is the shape of a s orbital? Good. Yep, this one's going to be circular or sphere. So if you have your carbon and your nitrogen, we'll just stick with that, bonded, this sigma bond is that first s orbital overlapping with each other. Okay, that's what causes that single bond to form, is the overlap of the s bonds, or of the s orbitals, excuse me. Okay. But when we have a double bond, right, what is the shape of a p orbital? Awesome. It's going to be a dumbbell. So it has those sphere shapes already, right, that are overlapping from that first bond. But then our dumbbell shapes are also going to be bonded, but they are going to be, right, they're not that's far away, they're much closer to each other. And so they overlap between your top and bottom portions of it. They kind of are attracted to each other, you can think of, and so they kind of lean towards each other, and that's where they overlap between there. Okay, and that's what creates the pi bond. Okay, so it's based off of the orbitals, based off of the shape, and it's based off of like the overlapping of those orbitals that causes the sigma and the pi bond. Okay, what other questions do we have now about sigma and pi bonds? Does that clear up some of the homework? Does that clear up some of the questions that we had? What do you mean by that, Samuel? I don't think you're going to have to draw a sigma or pi bond. You'll probably have to identify how many sigma and how many pi bonds are in a structure. So like the first one that we drew in black, you would have to count up how many sigmas and how many pi bonds you have in that compound, is my guess of what it would look like. Any other questions? Okay, I'll take silence as a no. Okay, so let's move on to bond polarity. Okay, so now let's talk about bond polarity. What causes polarity of a bond? What makes something a polar bond? Okay, I like those. I like the idea of both of them. We're just looking at, like, say, carbon and oxygen. Is this going to be a polar bond? Is carbon and oxygen a polar bond? Yes. Why do we say yes? Why do we think it's yes? Which one is more different elements? Yep. So usually when you have different elements, that's going to point towards it being a polar bond because each element has a different electronegativity. Awesome. Great answer, Brock, right? So oxygen is going to be more electronegative than carbon. Electronegativity means that that electron wants those electrons more than the other one. So we show bond polarity by saying, okay, the electrons are going to spend more time towards that oxygen atom. And so we point the arrows towards the oxygen, and that leaves behind a partial positive where carbon is. So oxygen's now partially negative and carbon is partially positive. And I think that little line on the side, like here, looks like a cation. And that kind of tells you, okay, carbon's going to be a little bit more positive than oxygen would be. And this is due to electronegativity differences. Okay, so that's what causes a bond to be polar. Okay, so I believe someone also said that like it has to be non-symmetric, right? This is non-symmetric due to the different elements that we see. But when we talk about molecular or molecule polarity, that's when it gets a little bit more important to look at the symmetry of the whole molecule. Okay. Any questions on bond polarity, what we've covered so far? Does that make sense why something would be a polar bond? It's a delta, so it's a partial. It's like a lowercase delta. Okay. Yep. So yes, Ethan. So the only time that we say that two elements that are different and are not polar is a carbon and hydrogen bond. So that would be when hydrogen is bonded to carbon. These electronegativities are so close that it's essentially nonpolar. So even those are two different elements, this one is the only nonpolar bond. The only time something else can be nonpolar is if the element is bonded to itself. So if chlorine is bonded to chlorine, I don't know why it keeps doing that. If chlorine is bonded to chlorine, then that would make it nonpolar as well, because there's no difference in electronegativity because it's the same element. Okay, so both of these are nonpolar. Yep, so the difference in electronegativity makes the bond polar. Does anyone know the periodic trend for electronegativity? What happens as you go across the periodic table? Good. Yep. So as you go across periodic table, okay, as you go across, electronegativity increases. What happens as you go down? Good. Decreases as you go down. Okay. So your most electronegative element is going to be fluorine because it's the most to the right and the most up on the periodic table. Going up on the periodic table. Yep, as you go left to right. So fluorine is the most electronegative because you're going left to right. HC is nonpolar because their electronegativities are so similar that it's essentially nonpolar. There is no difference in electronegativities. And then Samuel asked, is it true that the further away on the table, the more polar? If you have like fluorine attached to sodium, right, that becomes so polar that it's an ionic bond, right? So those are very far away. It's so polar that the fluorine atom just takes the electron from sodium. But if it's just looking at your non-element section in that top right corner of the periodic table, like your carbons, your oxygens, your fluorines, the farther away those are, the more polar the bond would be. So the only reason we say that H and C are nonpolar is because you can find values for electronegativities. You won't be given those unless you absolutely need them. So just go based off of the trend, right? If something's more to the right and more up on the periodic table, it's going to be more electronegative than its counterpart. Okay, so I guess I can show you my chemistry tapestry. Right, if we're looking at the periodic table, anything more up on the periodic table is going to be more electronegative, and anything more to the right, I guess, is this case here, that is going to be more electronegative. So for Adrian, that's just saying that sometimes the electronegativities are so different, it becomes ionic. So, right, when you have a metal and a non-metal, the electronegativities are so different that it becomes ionic. But when you're just looking at a metal to a metal, those will be polar, and that will just show the dipole moment, which is that arrow that we drew for the carbon and oxygen. Okay, what other questions do we have? Right. Remember, for polar bonds, you just want to trust your trends. No, so NH would be polar. NH would be polar. Right? If we're looking at the periodic table, it goes carbon and then nitrogen and then oxygen and then fluorine. Okay, so is nitrogen going to be more or less electronegative than carbon? It's going to be more, right? More I'm just going to, right, more electronegative. So if hydrogen can be replaced here, right, this is also hydrogen, there is going to be a difference in electronegativity between hydrogen and nitrogen because nitrogen's more electronegative than carbon. There is, but you don't need to worry about it. You just need to know that carbon and hydrogen is a nonpolar bond. Everything else, if it's a different element, will be a polar bond. The only way you can really know how small it is if you have values, and you won't have values, most likely. Sam, I don't know what that question is. But if we have time to it, I could definitely go to it and review it if it becomes a like a topic we discuss. Let's pull that up on my computer real quick. Yeah, we can talk about periodic trends and then we'll go over that a little bit. Okay, what other questions do we have on bond polarity? Okay, let's talk about Lewis structures a little bit now. Okay, this will talk about shapes. We'll talk about we'll talk about shapes. We'll talk about molecular polarity. We'll talk about shapes, including like molecular and electron domain geometry. Okay. So let's use an example in order to talk about all of this. Let's look at NO3 minus. Okay. When we want to draw a Lewis structure, what's the first thing we need to do? Yep, we need to count the valence electrons. So how many valence electrons are in NO3 minus? Yep, I like 24. Oxygen has 6 valence electrons and we have 3 of them. Nitrogen has 1 valence electron, and then we have, nitrogen has 5 valence electrons, and then we have 1 additional electron from this minus as the charge. So we have 24 total. Okay, what's next? What's the next thing that we do? Good, so we need a skeletal structure. What goes in the center? Good, nitrogen and the least electronegative will go in the center. And then we'll connect our outside atoms with a single bond. And that's going to be our oxygens. How many sigma bonds did I just draw? Awesome, right? We drew 3 sigma bonds because we have 3 single bonds. Great. How many electrons did we use? Awesome. How many do we have remaining? Awesome. Where do those 18 electrons go? Good. And are they going to go as bonds or as lone pairs? Awesome. Okay. Okay, what do we check now? What do we do next in our structures? Good. Yeah, awesome. Right now we're going to look at for the octet rule. We want to make sure that all of our elements have 8 electrons. Okay. Do all of our elements have 8 electrons? No, which one does not have 8 electrons? Good. Nitrogen doesn't, right? So what do we do in order to give nitrogen a full octet? How do we get it to have 8 electrons? Good. We need a double bond, right? We ran out of electrons to use, and so we need a double bond with one of the oxygens. So this will now become okay. Now, how is our octet rule? Is everything happy? Yep, everything is good to go now, right? Each of our oxygens have 8 electrons, and then our nitrogen also has 8 electrons. How many like where can have more than 8 electrons? Yep. So anything in the third row or down. So as you go, like if you go on, so if you go from period 3 to period 4 to period 5, like all of those are able to expand its octet and have more than 8 electrons. So since nitrogen is in the second period, we cannot expand its octet. So it can only have 8. But if we had phosphorus or sulfur that's in the third period, those can have more than 8. Xenon can have more than 8. That's usually one that pops up. Just trying to look. I think sometimes they put bromide at the center. That one can have expanded octet and all that stuff. Even chlorine can have more than 8. But that's really only if it's in the center of the molecule. If it's on one of the outside atoms, it will usually only have 8. Samuel, can you explain your question a little bit more, like why we used the extra 18 to do the valence electrons of oxygen, and that used up all 18? So that was the dots on for the question or for the structure on the left. But after we used up all 18, nitrogen didn't have a full octet, but we had already used up all of our electrons. And so we had to use a double bond. And so that created just one less lone pair. So you always want to fill your outside electrons first, or your outside atoms with electrons first. And so since we did that for oxygen, all 18 were used. And so there are no extra electrons to put as lone pairs on the oxygen or on the nitrogen. We had to take one of the lone pairs from oxygen and use that as a double bond to make nitrogen a full octet. Yep, and so we can go over polarity and formal charge with this one as well. Okay, so now the structure that has the one double bond and 2 single bonds is going to be the structure that we're going to work with. How many single or sigma bonds are in this structure? Good. We have 3 sigma bonds. How many pi bonds are in this structure? Awesome. Okay. Can this structure experience resonance? Yes. And why does this structure experience resonance? Good. So we have 3 oxygens and not all of the atoms are the same, right? So resonance means that we can draw this structure with the double bond on this oxygen instead. Or we can draw it on this bottom one. Okay, so there's 3 spots that we can put this double bond on our structure. Okay, so it's like, it looks like it's hopping around the structure. Okay, that's resonance. You can have the same structure, but the bonds are just laid out in a different way. Okay, so resonance exists for this one. That's only going to be for the central atom. And we'll talk about that in a second once we go over like polarity and formal charge. Okay. So my next question is, do we have any polar bonds in this structure? Do polar bonds exist in this structure? Yep. And where do we point our polar bonds? How do we draw our dipoles? Okay, so we're going to draw, our dipoles from N to oxygen. Oxygen's more right on the periodic table, and so it's more electronegative. And so the electrons are going to spend more time towards that oxygen rather than that nitrogen. Okay. Any questions on dipole moments here? Okay. Let's talk about the shape. The shape has how many electron domains? Dipoles are the arrows the blue arrows that we draw in, showing the difference in electronegativity. Okay, so then I asked how many electron domains there were. We said that there were 3. Okay, this is how many like sections of things you have, right? Think about how many bonds you are making, how many different sections of bonds you're making, and any lone pairs you have. So we have 1 electron domain, 2 electron domains, 3 electron domains. Okay, so you have 3 electron domains here. What is the electron domain geometry for something that is 3 electron domains? Good. This is trigonal planar. Oops. So if we were to draw a triangle, it would be our nitrogen and then our oxygen, and our oxygen. Okay, that's what it would look like as a structure. You could put it flat down on your piece of paper and the whole molecule would be on that paper, right? So that's planar. It's in a triangle, so it looks like a triangle, so that means trigonal planar. What is its molecular domain geometry? Good, it's the same. It's also going to be trigonal planar. Okay, there are no lone pairs in this structure. And so it's the molecular domain geometry is not going to be different from your electron domain geometry. It's different from T-shaped. Yep, so good question. So electron domain geometry is just looking at like your umbrella term, right? So you can either have 2, 3, 4, 5, or 6 of the electron domains, okay? From there, if you have if you have a lone pair as one of your electron domains, then your general structure is going to be distorted because the lone pairs take up more space than a bond would, right? Think of a dog on a leash, right? Between the owner, the dog can only move where that leash is. If it did not have a leash, then it can roam a little bit farther. It can take up some more space, okay? So your electron domain geometry gets distorted when you have lone pairs, causing your molecular domain geometry. Okay, and then if you haven't looked at my practice problems, question 19 is a chart filling out the different electron domain geometries and the molecular domain geometries. And so you can kind of group those shapes based off of what your electron domain geometry is. Jackson, good question. A double bond or a triple bond will always count as one electron domain. It just needs to be close. It might be a drop-down menu too. I'm not sure since it's an online exam. But it shouldn't be too, you don't worry about spelling. I'm also not very good at spelling, so I understand. Okay, any questions on shapes or anything? Any questions on anything we just covered on Lewis structures? Y'all seem to have drawing a Lewis structure down pretty well. It's just any questions I asked after that. Yes, so the electron domain determines the shape, that's one shape. And then the molecular domain geometry is then taking into account your lone pairs, okay? So if we had something like, okay, if we had these three compounds here, what is the electron domain geometry for each of these? What is the electron domain geometry? Okay, good. So these are all tetrahedral. If we look at, I guess I'll highlight them, right? If we look at the electron domains, we have this 1, 2, 3, 4. Electron domains for CH4. We have 1, 2, 3, 4. For your NH3, and then 1, 2, 3, 4 for your H2O. Okay, so each one of these has 4 electron domains. 4 electron domains means that we have a tetrahedral electron domain geometry. Questions on that? What is our molecular geometry? Going from left to right. This one's also going to be tetrahedral. Awesome. Okay, awesome, everyone. So your first one, your CH4, is still going to be tetrahedral. There's no electron domain, or there's no lone pairs, and so your electron domain geometry is not distorted. When we come to NH3, we now have one electron domain. So usually they're all at 109 degrees between your tetrahedrals, but this time the lone pair is going to take up more space, and that's going to squish your remaining three closer together. Okay, so if you think about a tetrahedral almost as a tripod situation, right, you're going to have your three legs, and then you're going to have the one portion that's sticking straight up, right, like maybe where your phone is attached. This is now taking your phone off of it, right? So you just have the legs left on your tripod, and that's going to smush them a little bit closer together once that lone pair is there, because the lone pair is going to take up more space. So now it still looks like a triangle because we have that triangle base, but it's no longer just plain 2D. It's still in this 3D shape. So that's why it's trigonal pyramidal, because we have 3D, or this third dimension, associated with the shape still. Okay, then when we talk about bent, this is now taking one of your feet off of the tripods. So now you just have 2 feet left on your tripod. It looks bent. It's just that V shape that we look for. And those 2 lone pairs are now going to take up even more space than just the 1 lone pair would. Okay, what other questions do we have based off of this geometry stuff? Does this feel a little bit better? So tetrahedral is going to be per 4 electron domains. Square planar is when you have 6 electron domains and 2 of them are lone pairs. Tetrahedral is 3D, where square planar can fit 2D. Any other questions on shapes, Lewis structures, polarity? What do you mean by will 2D be asked? Like, she might ask you about trigonal planar. She might ask you about square planar. Yeah, I would memorize your shapes, definitely. The difference in bent shapes would just be how many electron domains there are. So, right, you can have bent for 3 electron domains, and you can have bent for 4 electron domains. So that's just going to they're still considered bent. You don't really have to distinguish them as long as you just call them bent. Yep, absolutely. Sorry, my pencil just quit out on me. Are you talking about for oxygen, Samuel? So hydrogen can only ever have 2 electrons. So you can't put those lone pairs on the hydrogens. And if we didn't have those lone pairs, then it wouldn't have a full octet. And so that would cause some issues there. But if the lone pairs were just another bond or something, then it wouldn't be bent. It would be a different shape. Let's do that one. Let's do. Okay, let's try XEF3. Okay, so Ethan asked a question, could you possibly do a practice one where you figure out Lewis structure, polarity, electron domain geometry, and molecular geometry? So that's what I want you to find. I want you to find the Lewis structure, any polarity between the bonds. Tell me if the bonds are polar and if the molecule is polar. Tell me the electron domain geometry, and then tell me the molecular geometry. And I'll go in and answer some questions as you're working. So Brock, your trigonal bipyramidal would have 90 and 120-degree angles. You also have that 180 between the two of them, but that is taken into account for the 90, so you don't necessarily have to specify the 180. Xe would have 8 valence electrons. And then were there other atoms other than H that have the octet rule exception? That there is. It's only bromine. There's only beryllium and boron. Beryllium is the 4th element and only wants 4 electrons. And then, or is happy with 2 bonds, right? So it's just Be and 2 single bonds. And then boron is happy with 3 bonds or 6 total electrons. Yeah, Brock, I think for your exam, you just need to know the 2. Probably, yes. Sorry. There should be a minus charge. I forgot it. Sorry. Okay, so just for the sake of time, I started going through and writing the structure. You should have 30 total valence electrons. You use 6 by combining or by bonding all of your fluorines, leaving you with 24. You use 18 to fill up the octets of fluorines, and then you have 6 left over. All 6 of those can go on xenon because xenon is in the 5th period. Yeah, the 5th period. It's able to expand its octet, and so it can take on more than 8 electrons. What do we have any polar bonds here? Yep, we have 3 polar bonds. How would we draw those in? Yep, so we're going to go from the Xe towards the F. Okay, fluorine is more electronegative than xenon. And so since there's a difference in electronegativities, right, we have 2 different elements, that's going to mean it's going to be polar. So all 3 of these will have polar bonds. You point towards the fluorine because that one's more electronegative. Yep, go ahead.
Was the entire element non-polar because they cancel out the entire molecule?
Say that one more time.
Molecule polar or non-polar?
Yes.
They cancel out.
So now we have to look at the electron domain geometries and the molecular geometries to determine if the molecule is polar. Okay, so what is the electron domain geometry of your structure here? How many electron domains do we have? We have 6 electron domains. 3 of them are in a single bond. 3 of them are in a lone pair. Good, right? So we have an octahedral. We have an octahedral shape, right? 6 means octahedral shape. How many lone pairs do we have? We have 3. So what does that make this shape for molecular geometry? Good, this is going to make it T-shaped. Okay. What questions do we have about being at the electron domain as octahedral and then the molecular geometry as T-shaped? Okay. So molecular geometry takes into account the lone pairs, right? You're looking at how the molecule is now bonded according to this, now according to what's remaining, right? The lone pairs are what's going to distort the electron domain geometry, causing this molecular geometry. Okay. So if we're looking at this in terms of 3D, you would have your Xe in the center. You would have your fluorine. You have a lone pair over here, a lone pair over here, a lone pair over here, and then your F over here. I guess make it look a little bit more like a T. Okay, so now if we have our shape in 3D, we always have to think about this in 3D. This is pointing out this way for your lone pair or for your dipole. This way and this way. Okay, this is no longer symmetrical. Okay, no longer symmetrical because if you think about this pulling on a rope, you're going to have 2 going up and down. but then you're going to have one pulling to the right. And since it's being pulled to the right, it's no longer going to be nonpolar because those lone pairs distort the structure, causing it to be polar. If you see something with lone pairs, it is most likely going to be a polar molecule. Okay, so that's a good thing to know. If it has lone pairs, it's most likely going to be polar. If we go back up to your NH3 and your H2O, both of those are polar molecules because your lone pairs distort the structure, causing the dipoles to be causing the dipoles not to cancel out from each other. Okay, so this one here, your lone pairs cause your dipoles to not cancel out, therefore creating a polar molecule. Okay, what other questions do we have based off of this information now? So even though it might look symmetrical the way that I drew it on my paper 2D, you have to think about it 3D as much as possible. So there would be no resonance in this structure because they are only bonded by single bonds. You need to have different bonds in order to have resonance. So you really only see resonance if a double bond or triple bond is present. Shape names will not be provided, so you should know them. Yep, lone pairs do not count for resonance. It only counts for if you have like a single and a double bond. You're not moving around the lone pairs, you're moving around the bonded electrons for resonance. What other questions do we have? There is no 2D name for this. It's either going to be octahedral or T-shaped. Yep. Okay, so it is 2 o'clock. I'm happy to just look at the announcement that she made and just kind of quickly go over the gases that she talked about since I didn't get to it today for this hour. So I will do that real quick for y'all. Okay, so when you're using gas stoichiometry, this is when you're using making sure that you like either have a solution or something you might have, and so you're trying to find the limiting reagent, or you just need to use more stuff before you get to PV is equal to nRT. But always remember that your coefficients determine your molar ratios, and you have to be working in moles in order to get to PV is equal to nRT. And that is only for gases. So if you have something that's liquid, that doesn't count in PV is equal to nRT. That doesn't count for your gases or your stoichiometry for gases. Kinetic molecular theory as relates to molecular speed and frequency of molecular collisions. So we look at kinetic molecular theory. The higher the temperature, the faster your molecules are moving. And so if your molecules are moving faster, they're creating more collisions. If they're creating more collisions, they have a higher pressure. So the higher the temperature, the higher the pressure of that system. And that's because your molecules now have more energy, allowing them to be moving faster. The simple gas laws, this is just your P is equal to V, or PV is equal to PV. Your V over T is equal to V over T, or your P over T is equal to P over T, right? Your Boyle's law, your Charles law, your Avogadro's law, that stuff that way. Hey, I do ask a couple of questions just based on the relationship in those practice problems I gave you. So if you want to look at those and then you have any more questions, feel free to ask me those. But in general, as pressure increases, volume decreases. As volume increases, temperature increases, and as number of moles increase, the number of the volume increases as well. Look at the formula sheet from the mock exam she gave you, and that should be a very similar formula sheet that you will be getting. I do believe the combined gas law is on there, and definitely the PV is equal to nRT is on there as well. And then lastly, the effusion of gases. So the rate 1 over rate 2 is equal to the square root of molecular rate 2 over molecular rate 1 equation. This is just saying that the faster the molecule that is lighter. So if we look at oxygen gas in comparison to xenon gas, oxygen, the lighter molecule, we will effuse faster than the xenon will, right? The smaller the molecule, the faster it can move. And so that's what has to do with your effusion of gases in that rate equation that she gave you. That rate equation is given to you on your formula sheet. So if you see something with rates or something, how fast something is moving, it should point you towards that equation. I believe there is a mock exam question on that too. So that's a good place to look as well. And that is it from chapter 5, which is like the gases stuff that we didn't get to talk to today. Okay, that was a lot of talking in the last 4 minutes, but this will be recorded. This will be posted. You are allowed to go back and watch this again. I'll make an announcement about it once I'm done with my answer key as well. I just have 2 or 3 questions left, and then I can post that. So when that's done, this Zoom will be done, uploaded, and then I will send that along as well. Do we feel better? Worse? I don't know. Was this helpful a little bit? Okay. Okay. Okay, cool. Great. If you have any questions, I am around for the day. I will answer them before I go to bed tonight. I am a grandma. I will be in bed probably by 10 o'clock though. So if you have any questions, please just email me before then. Yeah, someone just asked me if I could put like steps on how I solved the problem. I do like follow it out and do all my work stuff. I don't just give you the answer. So hopefully you can see where I went and did those problems as well. And then I do know that if you look at those practice problems for the de Broglie wavelength, I forgot to give you a velocity. So I'll just include that in my answer key. I'll make one up and then do that. Other than that, I should have about an hour and then everything will be there for you to get ready. Good luck tomorrow. Get a good night's sleep as well. Sleep is important. You're learning a lot. Allow your brain time to recover and remember everything that you studied. Have a good breakfast in the morning. Make sure that you are feeling as best you can. If you do good, you feel good. Or if you feel good, you do good, and all that stuff in between. So have a wonderful day. Please let me know if you have any questions. I'm happy to help throughout the rest of the day and even into tomorrow as well. And with that, I'll let you get back to studying or going to make some lunch or anything like that. And have a great day. Thank you so much for attending too. Yep, any questions from your homeworks are going to be good ones. Your mock or your quizzes are the best place to study first, and then your homeworks as well. I'm happy to help, so thank you so much for doing this. I'm happy that you at least got some benefit out of this. I know it's a chaotic hour. Alrighty, thank you everyone.